Hello, and welcome to the Geodig 2023 workshop for digital rock physics. My name is Sven Linden, and today I'm going to guide you through the second part of this workshop. The workshop is split into two parts. In the second part of this workshop, we will predict absolute permeability and learn how to include the effects of microporosity on permeability in a rock sample. Then we will introduce a workflow to predict permeability of a whole rock core. Finally, we show how to do two-phase flow simulations, including mercury intrusion capillary pressure using one of the digital rock physics geo apps, followed by primary drainage, forced imbibition, and finally relative permeability using the new Zatodic graphical user interface. As already mentioned, in the second part of the digital rock physics workshop, we will focus on the computation of absolute permeability, capillary pressure, and relative permeability on a segmented Gilder-Hauser sample. We will use the module FlowDig to compute the absolute permeability of fluid flow fields using the Navier-Stokes, Stokes-Brinkmann, or Darcy equations. On the right-hand side, a 3D representation of a Gilder-Hauser sandstone with its computed corresponding flow field is visualized. With GeoDict, important information about digital rock samples and fluid flow behavior can be gathered. We can also consider the effect of microporosity on permeability. This is especially useful when the resolution is not sufficient to display the pores within a structure correctly. But I will also show you an example for that case later. Further applications are enhanced oil recovery, groundwater aquifers, hydrogen storage, or CO2 sequestration. The solvers of GeoDig are well known for their performance and accuracy. In this workshop, we will use the Lear solver to compute the fluid flow. It uses an adaptive grid structure, as shown on the image at the right-hand side. This reduces memory demands and improves the speed of a solver. Therefore, this allows us to compute the fluid flow fields on very large structures, for example 4000 voxels to the power of 3. Just few words about the boundary conditions in flow direction. On this slide, the effect of the boundary conditions on permeability is displayed. As you can see, permeability is artificially reduced by choosing the pure periodic boundary conditions without inlet and outlet. This boundary condition is not suitable for rocks and should not be chosen for this application. You should either choose symmetric boundary conditions or periodic boundary conditions with inlet and outlet, which is also the default in GeoDict. The number of voxels at the inlet and outlet should be larger than the largest through pore, such that it does not introduce artificial pressure drop. In this overview, the possible combinations of boundary conditions in flow and tangential direction which are suitable for rocks are displayed. As you can see, the default settings of FlowDig allow starting the computation of rock permeability right away, without changing of the boundary conditions. Nevertheless, you can manually choose the boundary condition which fits your setup. In this part of the workshop, we assume that importing a CT scan, doing image processing, and segmenting the gray values into different material IDs is already done. Therefore, we start by loading an already segmented rock structure. Go to Load GDT and select the Workshop Gilder-Hauser Sandstone Core GDT file. Then we go to the 3D visualization to have a closer look at the loaded rock structure. The segmentation consists of 3 phases. The invisible material ID 0 is a flow cell, which we do not want to consider in our simulation. Material ID 1 is our pore space filled with water. Material ID 2 is our solid phase quartz. Next step is to crop a small part out of the whole structure. To do this, go to the Structure tab. And here we use the clipping sliders to select a proper subset which we want to consider in our later simulations. The crop should be small enough such that subsequent simulations can be performed interactively. So here I will select a 300 cubed subset. So now I pull on the clipping sliders a little bit and select some part in the middle of a structure. To make things more easy, we can also enter specific numbers. Here I will set clip X from 300 to 600, clip Y from 300 to 600, and clip Z from 100 to 400. Then I use the geodig command crop. Go to the status section, right click on structure, process, and now crop. Press the structure clipping, use the structure clipping button to use the clipping values from the visualization. Press the 1 button to crop the structure. Next step is to reassign material IDs such that material ID 0 is the pore space and material ID 1 is the solid phase. Go again to the status section, reassign material ID. So now we reassign material ID 1 to 0. Here we enable assign corresponding material. And we do the same for material ID 2. So material ID 2 to 1. Then we click on the color and visibility sidebar, and we change the color of a quartz from red to gray. Now we want to perform a single-phase flow simulation to predict the permeability. To do this, we use the FlowDict module and switch to it by predict FlowDict. The permeability can be predicted using two FlowDict commands, Stokes-Brinkmann and one of the new FlowDict commands, DarcyFlow. Stokes-Brinkmann is used for micro CT scans with resolved pore space with existing percolation paths, and DarcyFlow is used, for example, for medical CT scans where most of the pores are not resolved. We choose Stokes-Brinkmann and open the solver dialog by pressing the Edit button. In the Considered Material tab, one can see and change the materials and their associated material IDs. In this case, water has the material ID 0 and quartz has the material ID 1. You can change, for example, water by clicking on it, and, for example, use air or some other fluid. But we will keep with water and close the dialog. All settings in this tab are fine, and we switch to the Boundary Conditions tab. The computation directions decide for which direction we want to compute the permeability. That means which permeability column in the tensor is computed. Here we leave it at the Z direction. We have already discussed the boundary conditions in flow and tangential direction. The default periodic with inlet and outlet and flow direction is fine for rock structures, so we can leave it. Here in this section we can prescribe a pressure drop and the solver computes a mean velocity, but it is also possible to prescribe a mean velocity or flow rate and the solver computes a pressure drop instead. You can also set the slip length to a value larger than 0 for nanopore applications. Next step is the solver tab.
where we have a choice between free flow solvers EJ, Simple FFT, and Velier solver. In this workshop, we use the Velier solver. We can leave the stopping criterion as it is with error bound. I will say a few words about this boundary condition later. But now have a look at the parallelization option. If we click Edit, we can now change the number of cores used for the parallelization. The default is local maximum, and it uses the maximum of available licensed cores, in this case 8. Velier has two special speedup methods called multigrid and the cool-off method. The multigrid method was introduced in GeoDict 2019 and speed up the computation significantly while using just a little more memory. The cool-off method was introduced in GeoDict 2022 and speeds up the computation very drastically for low porous rock structures, for example for 10% or below. But it is also very fast for porosities above 10%. The default automatic will automatically enable the method based on some heuristic. For example, it analyzes the porosity of a structure. But this method takes significantly more memory. So we will leave the default automatic. If you observe convergence issues on some structures, then you can also lower the relaxation value. If you set the relaxation lower than 1, then in situations where the simulation does not converge, you get the solver to converge. We do not have to change anything in this tab, and so we can leave the dialog by clicking OK. Press 1 to start the computation. If you want to get more details about the simulation status, then extend the progress bar. And you can also click this button with the arrows, and then this log window opens. Now you can see the convergence graph, which shows the computed permeability for the past iterations. The graph has two curves. The red curve shows the computed permeability per iteration. The blue curve shows a prediction based on the red curve, and this prediction is done by the error bound stopping criterion. If the red curve deviates relative to the blue curve by less than the specified error bound, then the simulation stops. The log on the right hand side shows many details about the solver, and this can be very helpful for debugging purposes. So if you observe any trouble with your simulation, then also send the log file to the support. The simulation should be finished in a couple of seconds. When the simulation is finished, then the result viewer pops up, which shows the simulation result. At the top, you can see the computed permeability tensor. You can change the units from meters squared to another unit using the options on the left side. For example, change them to millidarcy, and then click Apply. Now the permeability tensor is shown in millidarcy. This report also shows some other useful information, for example, the number of iterations, the runtime, or the memory consumption. The plot tab shows the layered pressure. That means the average pressure in the pore space per Z slice. It reveals if a structure has a bottleneck with a small pore throat. For example, here and here we have some steeper slopes. The velocity plot shows the average speed per z-slice together with its standard deviation. Now we want to visualize the results. The Create Videos tab allows you to create a video automatically. But in this workshop we want to do a manual visualization. And to do this we switch to the Flow Visualization tab. We select the flow field in Z direction and click Load. By default, all fields in the file are loaded, the velocity and the pressure field, and we can leave it. So we click OK to load the velocity and pressure field. We can now close the result window. So, to make a nice visualization, we first disable the structure. Then we go to the Volume Field tab and disable the flow visualization in the solid or in the quartz space. To do this, we disable and uncheck this checkbox. Now we just see the velocity in the pore space. You can now enable the transparency. Here with this checkbox. And observe a very nice visualization with just a few clicks. You can also show the pressure field by changing the color by option from velocity to pressure. Then observe a pressure drop from Z minus to Z plus. But now choose the velocity field again. Then switch to the Structure tab. Enable the structure again. And now pull on the Z clipping sliders to visualize the structure and the velocity field at the same time. Now you could save an image here to save an image with a current visualization. In addition, we show the case where unresolved pores or microporosity is considered in the flow simulation. We can use the Stokes-Brinkmann or the Darcy flow command. The Stokes-Brinkmann command should be used for CT scans where unresolved microporosity is present. The Darcy flow command is suited, for example, for medical CT scans with large voxel length and where most of the pores are unresolved, except some cracks. In this workshop, we just want to show this new command. So choose the Darcy flow command and click the Edit button. The simulation parameters are almost the same compared to the Stokes-Brinkmann command. In the Constituent Materials tab, we can now change the pores and solids to pores filled with water. So we click, for example, to water brine, choose porous solid, click on manual, and now we have a manual porous material filled with water. And we can do the same for material ID 1. Now we have two manual materials present in the structure. Then the permeability in the permeability tab can be entered. For example, to 1e minus 13 and 1e minus 12. Another difference between Darcy flow and Stokes-Brinkmann is the boundary conditions tab. This looks a little bit different, but it is still very similar to the Stokes-Brinkmann command.
To obtain the full permeability tensor, we would have to compute the fluid flow in each direction separately. That means in x, y, and z direction. The permeability tensor of the three main directions displays the respective permeability. In FlowDict, you may also visualize the fluid flow velocities for each direction. Using Geodict, you are enabled to include micro or nano porosity in your fluid flow computations. The microporosity is expressed by the Brinkmann term, together with the Stokes or Navier-Stokes equations. In this example, I would like to show how a fluid flow is computed, including the effects of microporosity in an Stellades carbonate. As you can already see in the gray value image, the Stellades rock has a lot of microporosity, which should not be neglected. But if a rock structure is obtained using medical CT scan instead of micro CT scan, almost no pores can be resolved. And when the Stokes part of the equation, the viscous term, can also be neglected. And when you arrive at the Darcy equation, where just the Brinkmann term is considered. In this case, workflow is similar to the previous one, but the microporous domain should be segmented as separate material, and the permeability of the microporous domain must be known. For example, you may obtain this by using other methods, like high-resolution focused ion beam SEM measurements. With this information, you can define the permeability of the regions and run a computation. When running a simulation on the Stellades carbonate rock, you may define an exemplary permeability of 1 millidarcy for the porous domains. I have visualized the result for LearSolver on the right-hand side of this slide. As you can see, the flow is not computed only in the pores, but also in material 01, which is the defined microporous domain. The resulting flow field also shows the lower fluid flow velocities in the microporous domains compared to the open pores. It is now possible to perform Darcy flow simulations in FlowDict. But why and when do we need Darcy flow simulations? Permeability computations are very challenging on segmented rock structures which were acquired by medical CT scanners. Usually, there are no resolved percolation paths through the structure, but just single cracks. With our Stokes-Brinkmann solvers, it would be possible to consider permeability value for each segmented gray value region. But unfortunately, the runtime of such a simulation is very high. The new Darcy solver can deal much better with this situation. Here, the Darcy instead of the Stokes-Brinkmann equations are solved, where the viscous term is neglected. Both EJ and LearSolver support this equation. The support of 256 material IDs in Geodict allows to solve the Darcy flow equations almost directly on a gray value image when a gray value to permeability map is available. If you don't want to lose information of a cylindrical pore sample, you can always calculate the fluid flow field of the entire core plug. By doing so, you should differentiate between the void space outside the plug and the pore space inside the sample. Set the void space as solid material in Geodict and start the computation of a fluid flow field. Since the permeability is computed over the area of the computational domain, one should remove the effect of the void voxels outside the sample. This is as easy as shown here. Just look up the volume fraction of the flow cell material from the Statistics tab. Calculate the core volume fraction as shown, and finally find the core permeability. In GeoDict 2023, we enable you to compute two-phase flow using the module ZatoDict. While we introduced the dynamic pore morphology method with GeoDict 2021, we developed the true contact angle method for GeoDict 2022, which extends the two-phase flow capabilities to the entire contact angle range from 0 to 180. In GeoDict 2023, we enable the user to consider mixed bitability and perform forced imbibition simulation directly in the ZatoDict graphical user interface, which is not possible before, but just using a Geo app.
Before we start with the two-phase flow simulation, we want to discard the cone flow field using the status section. And right-clicking at volume files, discard volume files. And we set the clipping values to the initial values. First, a Mercury intrusion capillary pressure simulation is performed. This kind of a simulation can be done as one-click solution. Go to the Geo app menu, Digital Work Physics, and here you can see a list of Digital Work Physics specific Geo apps, all gathered in one place. This is new in GeoDict 2023. Click on Two-Phase Flow. Then choose the MICP for Works Geo app and click Edit. We can leave all the default settings here, but one new feature of this app is the computation of pore fold size distribution using the Washburn equation. Click OK and run the simulation. Here, also extend the progress bar to get more details about the simulation status with its own convergence curve, showing the capillary pressure for the current mercury saturation. This will also take just a few seconds to complete the simulation. As you can see, a certain capillary pressure is required such that mercury is able to invade the structure. The result file shows different columns: the saturation for the invading and replaced fluid and its corresponding capillary pressure. Go to the Plots tab and see the computed capillary pressure curve. Here you can also see the mentioned pore fold size distribution. And it has a peak at around between 30 and 40 micrometer. But we skip the visualization of a mercury saturation and will do it later after primary drainage simulation was performed. So we click Close. Next, we perform a primary drainage simulation followed by a forced imbibition simulation using the new ZatoDict graphical user interface. For this, go to the ZatoDict module with Predict, ZatoDict, In this workshop, we will look at the capillary pressure command and the relative permeability command. So select the capillary pressure command and click Edit. The graphical user interface was improved significantly by rearranging options and removing the names wetting and non-wetting from the dialog to make it easier to set up simulations with mixed wettability. The Considered Materials tab is the first step. So, first thing we want to do, make sure that the contact angle mode is true contact angle. Change the interfacial tension to 0.03. Set the invading fluid to be oil. And now set the fluid in the pore space to be water 1. Below here you see the contact angle input, where the contact angles are now given with respect to the invading and the replaced fluid instead of the wetting or non-wetting fluid. Set the contact angle of oil to 140. Next, switch to the Situation Experiment tab. Here, a drainage simulation will be performed, since all contact angles are greater than 90 degrees. Leave the other options as they are. Oil must be connected to an oil reservoir and water can be trapped. Here, we do not need the dynamic pore morphology method. Next step is the Boundary Conditions tab. Set that oil invades from Z-, and now we allow that water can leave the domain through the other domain boundaries. In the Solver Parameters tab, there are 3 new options. First, the parallelization, which allows to set up the number of cores used for parallelization. Second, the new stopping criterion, stop at saturation. And the last option is the output option, where we can select which fields should be written in the pressure and saturation file. We leave the parameters as they are and have a quick look at the new Equations and References tab. It shows the Young-Laplace equation and gathers some important literature about the pore morphology method. Click OK to leave the dialog and press 1 to start the simulation. The convergence curve will look similar to the MICP experiment, but the simulation will end at a smaller saturation than 100% because water can get trapped in the structure. And here, again, the simulation will be finished in a couple of seconds. The result file is also very similar to the MICP experiment. If we go to the plots, we can see that we have some water residual that remains in the structure. One new plot can be inspected here, the layered saturation. We now switch to layered Z saturation because all invaded the structure in that direction. So this is new and shows the layered saturation for different slices and for different saturation states. To visualize the result, go to the data visualization. Here are 2 ways to visualize the data: the pressure and saturation file and the structure files. which were generated by the Zato-dig command. In this workshop, I would like to show a visualization with a pressure and saturation file by clicking Load. And here we also click OK. We click Close. And now I want to show you how you can visualize the invasion of oil. First, disable the structure. And then switch to the Volume Field tab. The invasion of oil and displacement of water can be visualized easily by pulling the threshold clipping slider. You see that at some point there is a breakthrough when the smallest pore flood is passed. Next, we would like to show how to perform forced immersion simulation considering mixed wettability. First, load a structure that is especially prepared for this application. So here, load the structure Workshop Gilderhauser Sandstone Cropped with all wet parts. This structure is a little bit smaller and contains 2 quartz material IDs. Then open the capillary pressure simulation parameters dialog. In the Considered Materials tab, we can now enter a contact angle smaller than 90 degrees for the water wet material and larger than 90 degrees for the oil wet material. First, we set the invading fluid to water brine, and the replaced fluid now will be oil. The water wet material gets a contact angle smaller than 90 degrees, for example 40. And the other material we get a contact angle larger than 90 degrees, for example 140. In the Saturation Experiment tab, one can see that now a spontaneous part and a forced part can now be simulated for the positive and negative part of a capillary pressure curve. Here we need the dynamic pore morphology method. Click OK and run the simulation. In this simulation, the special thing is the simulation starts at a positive capillary pressure and will change at some point to negative capillary pressure values. Here in this structure, it will happen at about 12.5%. It will happen here about this point where we have a transition, but it will take a few more seconds. Here, the transition from positive to negative capillary pressure happened. Click into the plots and observe the computed capillary pressure. Finally, we end this workshop and show how to start a relative permeability computation based on this forced inhibition. Choose Relative Permeability command. Click Edit, and in the Wettings Parameters tab, select from Simulated Wetting Process and select the capillary pressure result file. The number of points where relative permeability is computed is based on the saturation steps here in this section. You may increase it to 6. You can compute relative permeability for the water and the oil phase. The other settings are very similar to the floating settings. You could close the dialog with OK and run the simulation, but we leave it up to you since we approach the end of this workshop.